Hello, everyone. My name is Yue Wang. I'm a second-year doctoral student in composition at the University de Montréal.
Hello, everyone. My name is Meilin Wu. I'm a doctoral student in composition at McGill University.
We're very happy here to share our project, exploring musical creation through green-body digital musical instrument. We'll introduce our project in 5 parts. First part, the goal of the project. Second part, the system structure. The third part, the composition and the performance. Fourth part, the challenges. Finally, future work.
In the first part, I'll briefly introduce our project. We use brain-body digital musical instrument, or BBDMI for short. It connects muscle signals to real-time sound processing. In the past decade, many studies have looked at how these signals work in music. Our goal is to build a system that let us compose and perform music live. We use piano, flute, and shakuhachi to show how muscle signals can shape sound in performance.
About the second part, let's move to the system structure. In this project, we use a Pitalino drive to capture AMG signal from the performer. The signal are sent via Bluetooth to map AMG on a PC, where they are adjusting the turn into OSG signal. These signals are then sent to a Mac, where a Max MSP patch using the BBDMI package receives them and maps them to sound parameters for real-time audio processing.
Let's move to the third part. In this project, we balance both the creative and technical aspects. The technology inspired the composer, and the composer's feedback helped improve the system. The two parts influenced and supported each other throughout the project.
Here is the music created using this system. It's a piece for shakuhachi and electronics. In the performance, the left arm of the performer controls the granular size. The stronger the signal, the larger the grain size. The right arm controls the panning of the sound. Weaker signal shifts the sound to the left. Stronger signal move it to the right. Let's listen to the music.
In the fourth part, we'll talk about the challenges, both from a technical and a compositional point of view. From a compositional view, we faced three main challenges. The first one, limited performer movement due to the short cable. The second one, unclear gesture notation. And the last one, the need to design music based on body signals, not just sound ideas.
On the technical side, the Pitalino signal transmission is not always stable. Additionally, each adjusting process can be time-consuming and require considerable effort. In the future, we plan to simplify the connection process, shorten the adjusting time, and improve the sensor hardware to support fully wireless signal transmission. The ultimate goal is allow the performers to move freely and expressively without physical constraints.
Thank you for watching. If you have any questions, feel free to email us.
Thank you. Bye.
Bye.
Hello and welcome. This paper explores harmonic trajectories implementing modern music theory with modal interchange, revealing new possibilities of chord qualities and progressions with a 53 tonal equal temperament, which we are going to refer as 53TET. We worked on this project in collaboration with Ken Degernel, a researcher in the Algomous team in Lille, France, Bob Storm, the director of the Mosaic project, and I, David Dalmasso, a postdoc, and we are located in the Royal Institute of Technology, KTH, Stockholm, Sweden. Some of the research questions are how to extend the harmonic vocabulary available in pop music corpus to a more detailed pitch resolution framework such as the 3153TET, what kind of chords and nature exists in 53TET, and how to develop a computer application to navigate those harmonies and how these 53TET chords sound. Summarizing, the main idea is that those systems we have more interval qualities. For example, in 12TET we have minor and major, as we know in the third and, for example, in the seventh. And in 31TET we have subminor, minor, neutral, major, supermajor. And 53TET we have subminor, down minor, minor, up minor, neutral minor, neutral major, down major, major, up major, and supermajor. Many more options. So what we have done in the application is to propose a circular chart to edit the location of the nodes we are going to implement to make the chord constructions. As you can see, the zone related in the thirds and the sevenths shows all intervallic options that open up many new chord qualities and also closer approximation to just intonation of those frequencies that actually align well with the harmonic series. So if we take a look at the application, it runs inside Ableton Live in connection with a Max for Live object, which is a bridge that translates the events of the application into a MPE MIDI to any MIDI track. So that means that any instrument that we have that allows MPE can be used, like a piano or synthesizer, as I'm going to show you later. So the application has a grid scene that you can drag and drop chords. I'm going to show that, and also has a scene to navigate with the standard modes in this one, and also has a scene to play with melodies or with the kind of a configuration of a piano, and they can be also played with the keyboard of the computer. So this is the standard modes, and in this scene we can play with different configuration of the scale editor. But let's play with a progression. For example, we do 1, 6, 4, 5, 1, and you can see that we have synthesizer with new chord qualities, and we can this is modal interchange, so we are using parallel modal interchange, in this case Phrygian, now Aeolian, the next is relative Dorian. We borrow chords from Dorian, relative Phrygian, relative Aeolian, and relative Locrian. Every chord we click, actually we can edit the voicing. Sometimes we need the 7 also to configure the name. So let's play with other trajectories, and you can experiment with the application to any direction. So for example, if we try a new color, neutral third and neutral seventh, that this position also creates different chord configuration, and we are going to do the same 1, 6, 4, 5, 1. Thank you.
Hello, and thank you for joining this presentation. My name is Aditya Arora, and I'm presenting our paper titled Designing Sensory NIME for Autism, a design-led review and a synthesis of inclusive musical interfaces tailored for sensory modulation and emotional regulation in children with autism spectrum disorder. This project was developed in collaboration with Erika Tandoori, Stuart Favilla, James Marshall across Swinburne and Monash University. Sensory dysregulation is among the most prevalent features associated with autism spectrum disorder, affecting over 95 of diagnosed individuals. These disruptions manifest as either sensory overresponsivity with heightened sensitivity towards light, sound, or touch, and underresponsivity, which presents as diminished reactivity or repetitive sensory seeking. Critically, these sensory challenges are closely linked to difficulties in emotional regulation, social engagement, and cognitive functioning. As noted by Kern et al., sensory difficulties are not peripheral but instead deeply shaped with autistic individual embodied with an effective experiences. Despite decades of clinical intervention, mainstream sensory therapies such as SIT, sensory integration therapy, and MSE's multisensory environments demonstrate inconsistent efficacy. This NITA trial, a major randomized controlled trial, found no statistically significant improvement in behavior compared to usual care. Moreover, existing therapies model are often clinical driven, rigid, and environmentally static, lacking adaptivity and fluctuating sensory thresholds. This makes them difficult to personalize, especially for neurodivergent users with dynamic and situational sensitivities. In response, our study examines how NIME system, new interfaces for musical expression, may provide adaptive, inclusive, and responsive alternatives. We conducted a structured literature synthesis of 30 peer-reviewed NIME papers, ranging from 2015 to 2024, specifically focusing on those involving sensory engagement, interaction design for ASD, and adaptive multimodal feedback. A thematic synthesis approach was used to derive recurrent sensory principle across auditory, tactile, visual, and etc. domains, resulting in these three core and five design recommendations. Three emergent themes were: first, rhythm-based regulation. Many systems leverage rhythmic entertainment to support regulation and attention, with projects like Ollie, Musicane offering tempo-guided and immersive environment that synchronize neural and bodily rhythms. Theme 2, real-time adaptivity. Adaptive system using biofeedback and threshold modulation for environmental sensing adjust sensory stimuli, moment-to-moment mitigation, overstimulation, and preserving agency. Note examples include snake synth and Irdum's breath sensor piano. Theme 3, play-centered multisensory design. Interfaces like Westball and Boombox emphasize exploratory, non-goal oriented interaction. These promote engagement, agency, and meaning making through tactile auditory interaction and integration, making them away from compliance-based frameworks. Our synthesis generated five theme imperatives. First, in adaptive modulation, a system must dynamically adjust to ranging and changing sensory threshold in real time. Rhythmic anchoring, a predictable temporal structure, supports integration and internal regulation. Play-centered design encourages effective user-led exploration. Inclusive accessibility. Interfaces must be physically and cognitively adaptable. These findings form a sensory design heuristic for inclusive interface developed particularly relevant to NIME community. In alignment with these insights, we present Sonic Synth, a multisensory synthesizer, a MIDI keyboard for rhythmic input, 6 rotary knobs, and 4 arcade buttons for real-time modulation, Rainbow and MX patches for adaptive sound synthesis, a Raspberry Pi 6 running the audio engine, an Arduino controller managing external LED visual feedbacks, and future haptic outputs. Independent subsystems underpin the design, including adaptive profile switching, rhythmic co-regulation, modular controller, and a conceptual music decompression layer. This interface translates our research finding into a tangible tool for both autonomous and regulative and a co-regulative use. This work repositioned NIME system as therapeutically adjacent tool, not replacing clinical practices, but expanding the landscape of interaction for autistic users. We argue a shift from static intervention towards dynamic music interfaces, from behavioral compliances towards co-regulation and sensory literacy. Let the music become a language of regulation. We all invite you to read our full paper, a detailed insight into all 39 systems, their gaps, design, and the full sensory design heuristic developed to support inclusive